welcome everyone to the 2026 Photonics Spectra Summit Series. Thank you so much for attending the Raman Spectroscopy Summit, and in this session you will hear from Dieter Bingemann, a chemist and senior application scientist at Wasatch Photonics. Dieter earned his doctorate in chemistry and joins us with over 3 decades of research and industry experience in spectroscopy, analytical chemistry, and applied photonics. Today he'll introduce pocket-sized Raman solutions for real-world problems. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Dieter, we appreciate you for taking the time to join us here at the Raman Spectroscopy Summit.
Thank you so much, Jake, for your kind introduction and for organizing this Raman Summit and inviting me to it. Today, I want to tell you about a pocket-sized Raman system, some of the applications that have been done with it, and why it could be a good foundation for the Raman application that you might want to do. Two technologies have made enormous strides in the past decade. The first is automatic coffee makers. A cappuccino used to require specialist barista knowledge, but now everybody can just push a button and out comes the perfect cappuccino. The other technology, you might have guessed it, is Raman spectroscopy. Raman used to require specialist knowledge, but thanks to recent advances, everybody can now just push a button and out comes the perfect Raman spectroscopy result, like the cappuccino out of the coffee maker. This here pictured, and this one I'm showing you here, is the focus of my talk, the new XS Raman system from Wasatch Photonics. This is not just a Raman spectrometer, but rather an entire Raman spectroscopy platform, like a Raman Lego set that enables you to create your very own Raman solution. This Raman system is pocket-sized, yet it is scientific grade. It is powerful, yet it is easy to use. It's affordable, yet it gives you high quality spectra. Now, we all love Raman spectroscopy. That's why we're here. Raman recognizes molecules using their unique vibrations, basically by the way they wiggle. This is so characteristic that we actually call it a fingerprint. This is very similar to the way you can recognize a person at quite some distance just by the way they walk. And Raman is incredibly easy to apply. You just shoot your sample with a laser, basically, and the light that bounces back at you contains all the information that you need to identify these characteristic vibrations. Now, how cool is that? So with this unprecedented specificity and this unbelievable ease of use, Raman basically provides you an instantaneous point-and-shoot chemical analysis without any sample preparation. So it's no wonder that we all just love Raman spectroscopy. But Raman systems used to be lab animals, big, bulky, complicated, and expensive. Well, no longer. With this new XS Raman system, Wasatch Photonics packs the scientific quality of a benchtop system into a pocket-sized, truly handheld device. But despite the small size, this spectrometer is actually a completely integrated Raman system. This means it contains all the optics, the laser, detector, electronics, everything. All you need to do is to add your sample. It's basically the equivalent of instant lemonade powder, just add water, but now for Raman applications. The XS is about the size of a computer mouse. It is battery powered, it can communicate via Bluetooth. So it can easily be used with a smartphone app out and about in the field. And just like the coffee makers in the app, you just need to push a single button and the rest is fully automatic. Now, while you can think of this Raman system as a product, as is, I'd rather want you to think of it as a platform, a universal foundation, like an enabler for the Raman solution that you can build with it. And to turn this Raman platform into your Raman solution, you only need to add two things. The first of them is on the front end, one needs to couple this Raman engine with an accessory that matches the sample in your application. What do I mean with that? The accessory needs to be specific for your sample. That is, the sample type, the shape, the form, the size, the amount, you name it. This front end is really critical. In my experience, the sample accessory is really where one makes or breaks a measurement. Now, the middle portion is the Raman platform that I'm talking about today. And on the back end, one needs to extend the smartphone app with a specific spectral analysis that you need for your application. Because only your analysis can turn the Raman spectrum into the actual information that you want. This is part of your secret sauce. So with these two additions on the front end and the back end, you can turn this Raman platform into your Raman solution. It's like a match in Raman heaven. Now you might ask, Raman system this small, right? Truly, there must be a catch. Could this be any good? Like compared to the bigger guys shown here, can this little one really compete? For one, you might think, what about the signal? Well, the XS spectrometer is built using the same high efficiency, small f number, optical design like all the other Wasatch Raman systems. And sure enough, when I look at the Raman signal, this XS can easily keep up with the big shots. Okay, well, but spectrum to spectrum, you might wonder, how reproducible is this really? In other words, is this little guy really stable? Well, good question. And I'm really glad you asked. I was actually wondering the same thing. So I went ahead and recorded several hundred Raman spectra in a batch over the course of about half an hour. And I show here on the left the signal stability in time using ethanol as a sample. And on the right, I show the frequency stability in time using cyclohexane as a sample. And what I find is the standard deviation of the ethanol signal of about plus minus 0.1% shot to shot. And for the frequency, a variability in the position of the main cyclohexane peak of about plus minus 0.02 wave numbers. This stability is actually unbelievably good for any Raman system, large or small. To illustrate this stability differently, I also plotted the same cyclohexane spectra, but now as a false color image with the Raman shift on the x-axis and the time running upwards. So a good frequency stability now means that the vertical lines in this image are nice and straight. And as you can see, they really are. To tell you a little secret, we found that the key to the stability, both in frequency and intensity, is the tight temperature control of the excitation laser diode. Without this temperature control, the lines in this false color plot would look more like they were drawn freehand after, say, 6 espressos. All right, so signal, check, stability, check, but I also claimed that the XS is a scientific instrument. Yeah, what do I mean with that? Well, we've already seen that the unit has signal and stability of a benchtop system. And even though it is really small in the lab, you can actually still use it just like a benchtop system if you really want to. It connects via USB to the standard Wasatch open source GUI software. The software gives you full control over all parameters of the spectrum. It also has a full suite of calibration and post-processing options. And you get full access to the raw data after the acquisition. This full transparency is what scientists really want. And quite frankly, this is also what the application development needs. Speaking as the one who does data analysis every day, believe me, you will need access to the raw data, especially once you start looking into AI. So signals, stability, scientific. So where's the catch, you're probably thinking? Well, the laws of optics always demand a compromise. And for the XS, this means that the small size limits the optical resolution that is possible. However, once I actually test the spectrometer using Raman samples with known sharp lines like cyclohexane, toluene, or calcium carbonate, the Raman line width that I observe here, shown in purple, is still very comparable to that of the bigger systems. And more importantly, this width is still on the order of most typical Raman lines. And finally, when I'm actually comparing the Raman spectra from this system to those from the bigger spectrometers side by side, I really cannot see much of a difference. Allow me a brief aside here. I do have a lot of customers selecting Raman systems, and I have to say, resolution is very often overstressed. It's almost like it's a number that's easy to understand and that users want to hold on to like an anchor. But as your friendly neighborhood application scientist, believe me, there's only a few applications that really need the best possible optical resolution. One example for that might be the measurement of disorder or stress in semiconductors, which is looking at minor changes to the Raman line. But for the vast majority of Raman applications, resolution is really not critical at all. All right, so I hope I could convince you that this little spectrometer is actually surprisingly good. So let me get back to the applications that I had promised, because it really is the application where the rubber hits the road. I've already pointed out that to turn the XS into your Raman solution, one needs to add a specific front-end and back-end, a front-end accessory and back-end analysis, almost like a sandwich around the XS platform. So let's dive in and start with the front-end, the sample accessory. Here I'm showing you a few examples. So we have, starting from the left, a wave number calibration sample, a holder for sample vials or cuvettes, a holder for source substrates, and a free space lens. These accessories are exchangeable, and it just slide onto the front. Again, think of these accessories here in the picture as examples. The optical path between the instrument and the accessory is in what we like to call parallel space, which basically means for you that one has a lot of design flexibility to create a custom front end that matches your sample type. By the way, the different colors in this image here are not just for decoration. They actually indicate the laser wavelength. So it's 633 on the left, 785 in the middle, and 830 on the right. A little fun fact. The basis for the back end of your application is the smartphone app. I've already mentioned that the app and the spectrometer talk to each other via Bluetooth, and that all you have to do is push a single button as shown here, and the spectrometer and the app will do the rest. Why is there auto Raman function in the app? Well, believe me, nobody wants to fiddle with spectrometer settings using their fingers on a smartphone. So the spectrometer picks the best setting for you automatically. This actually makes the system real easy to use. One of the big issues with Raman, though, as you probably know, is sample fluorescence. The app therefore has a powerful fluorescence reduction option. If I, for example, want to measure a brownish sample, like this brandy or rum, a typical Raman spectrum will sit on top of a strong fluorescence background, like the spectrum shown here in the middle. The app, however, can completely remove this background in post-processing from the spectrum, and in the case of the brandy, will recover just the pure ethanol spectrum as shown on the right. Now, while such a clean Raman spectrum might look beautiful for geeks like you and me, but it is by itself, I have to admit, not yet the answer for your application. The actual information you need, the answer to your application question, must be extracted from the spectrum in the back-end analysis. And very often, spectral analysis falls into one of the following three categories. It could be a qualification, basically asking, does this look similar to typical samples we've seen before? It could be a classification, which is basically asking, is it this or is it that? Or it could be a quantification, which basically asks, how much is in it? Now, the clean Raman spectrum we record with the app contains the information to answer these types of questions. The answer just needs to be extracted in this analysis. And the example applications I show you will touch on all three of these analysis categories. As our first example for an analysis, I'll use a simple library matching. In library matching, the app compares the recorded spectrum against the small library that is provided by Wasatch. It then reports the closest match from the library and the score between 0 and 1, indicating how well the sample spectrum aligns with the reference spectrum. Now, one can also instead compare the spectrum against a much bigger commercial library. In the top right, for example, I've plotted the matching scores that I found for about 30 samples against the commercial Raman library from ST Japan, with scores ranging from 0.91 to 0.99. Finally, you can also just record and add your own custom reference spectra to a user library. So lots of options to work with. Where might this library matching be useful? For example, you might ask, well, if you have, say, a suspicious sample, like a white powder or some pills in a plastic baggie, could this possibly be some illegal substance, like cocaine or ecstasy or something? Well, rest assured, certainly not my samples. And as you can see, the app identifies the powder as some harmless citric acid, and the pills were just some mundane ibuprofen. But the small size also makes the XS real handy for some quick spot checks. Say you have a poorly labeled sample, like this lab manager's nightmare here on the right. Now, this lid says ethanol, or is this really methanol? You know, one letter can make a big difference. But for Raman, this really is no challenge at all. This sample here, for example, the app tells us is just some ethanol. That's real easy. You could also imagine using the XS for a quality check of some product. Yeah, if you have a spectrum of the pure substance in your library, how well does the spectrum of a new sample agree with this reference spectrum? Say, if the matching score drops below some threshold, you might conclude that the sample is not of good enough quality. For example, this glucose sample shown here on the right has a score of just 0.68. Much smaller than the scores of about 0.9 for the other glucose samples shown on the left. I want to mention, though, that I'm using library matching here for quality controls, really just as for illustration purposes. For an actual quality control, there are better analysis methods available. For example, one would much rather compare the test spectrum against a distribution, basically an entire collection of reference spectra, not just a single spectrum, like what I did here. For simplicity, using library matching. Now, a bit more challenging is the following application case. It is actually, sadly, not uncommon for questionable liquor to contain toxic levels of methanol. Why is that? Well, methanol is one of the compounds that's often used to render pure ethanol unfit for human consumption. Therefore, this now industrial alcohol is tax-free and much, much cheaper. This low price now in turn attracts counterfeiters, mixing the cheap industrial alcohol into counterfeit liquor, which then, of course, is toxic. This is actually a serious problem in a number of countries, and it kills or permanently maims those who consume this counterfeit liquor. Now, very low levels of methanol can actually occur naturally in a liquor. So there is some allowed, but not harmful legal limit for methanol. This limit depends on the type of liquor and where you are. And roughly speaking, to oversimplify a little bit here for clarity, this limit is on the order of roughly 0.5 weight% of methanol in a typical liquor. Now you might already guess where this is going. So here's the question. Can the handheld XS Raman system quantify these low levels of methanol in a liquor? Well, I wanted to find out, so I prepared calibration samples, recorded spectra, ran a regression analysis, and tested known and unknown samples. As you can see in the spectra on the right, the methanol adds a small bump on top of the shoulder of this characteristic ethanol double peak, which I sometimes like to call the Batman ears. While this methanol bump is pretty small, after some pre-processing, the calibration curve actually looks pretty good. That's shown on the top. In the end, I find a limit of detection of about 0.2 weight% methanol in liquor. Remember, 0.5 weight% was roughly the legal limit. So this approach does indeed look promising. And yes, as shown on the right, in my test samples, I detect the expected levels of methanol with pretty good accuracy. I also tested the method with commercial vodka or fruity liquors, as pictured on the left, and again, the method worked really well. So even a challenging quantification, which quite frankly is not the strength of Raman, is still possible with this small Raman system. The 0.2 limit of detection that I find here is sufficient in this application to identify liquors with toxic levels of methanol. However, you can probably think of quite a few applications that would require a much lower detection limit. So you might ask, can one also detect traces of a compound in a sample with Raman? Well, Raman is not known for strong signals, and the fraction of a percent we find here is typically about the limit. But one can amplify the Raman signal using a surface effect. This is abbreviated as SERS, which stands for Surface Enhanced Raman Scattering. SERS substrates contain nanometer-sized structures that generate this effect. These structures could, for example, be just some gold nanoparticles. These particles gather around the analyte and form tiny clusters. These clusters then, in turn, amplify the Raman signals by several orders of magnitude. This way, SERS allow us to detect contaminations to much, much lower concentration levels. So I just had to try out SERS with this XS Raman system. My sample here that I'm using is melamine in water. I'm using commercial SERS substrates that contain vacuum deposited nanoparticles on a pad. And I use the spectrometer with a SERS accessory as shown in this picture. With this SERS setup, I was able to detect melamine in water down to about 100 parts per billion, as seen by the spectra on the top. For comparison, as I show in the bottom, without the SERS effect, in the solution itself, I lose the signal below about 1,000 parts per million, or in other words, below 0.1%, which is again about the typical Raman limit in the solution. So the SERS effect improves my detection limit by about 4 orders of magnitude, and it works just as well with this small Raman system. Now, the final application example that I want to present is the result of a very close and fruitful collaboration between Wasatch Photonics and the research groups of James Deere, Karen Falls, and Duncan Graham at the University of Edinburgh and the University of Strathclyde in Glasgow. And their research, quite frankly, could be a real game changer in medical diagnostics. These research groups have developed lateral flow strips to detect early signs of drug-induced liver injury, which is abbreviated as DILI for short. The liver injury is caused by an overdose of acetaminophen or paracetamol, whatever it's called where you live. Such an overdose often happens by accident, for example, when taking combination drugs that contain multiple active ingredients, with one of them being the acetaminophen. Okay, why lateral flow? Well, lateral flow strips are cheap, the test is quick, and it can replace a slow lab test in the screening stage. This method is actually already in the clinical trials, and it is successfully being used by nurses in a hospital. So how does it work? Well, this lateral flow assay in many ways is similar to the COVID test strips that you know. Like those, it uses gold nanoparticles and antibodies, but unlike the COVID tests, the DILI strips use a Raman reader instead of a simple visual check. This is because the concentration of the detected analyte is very low, and the test lanes on the DILI strips are very faint, as you might be able to see in the picture on the top. So a Raman reader measures these lanes and the reader is pictured in the middle. This spectrometer actually focuses the laser to a line instead of a point to better match the shape of these lateral flow lanes. With this method, one can now quantify extremely low limits of the disease marker protein in a single drop of blood. This protein is basically the liver's cry for help and indicates the presence of the drug-induced liver injury. Now here comes the real exciting part. This lateral flow detection, like I said, uses gold nanoparticles, Raman markers, antibodies, and this Raman reader. It is not limited to just this DILI detection. This is actually a very generic approach. With other antibodies or even oligonucleotides, similar lateral flow strips with the same Raman reader could detect other disease markers in the blood. Just imagine what this could mean. I, for one, would actually not be surprised if in the not so distant future, Raman will be an essential tool in medical diagnostics and early disease detection. All right, after this daring prediction, let me get back to the facts and try to give you a little summary of what we just looked at. I showed you 5 very different example applications for this Raman system here, like identification, quality control, food counterfeiting, trace detection, and medical diagnostics. Again, with these examples, I really just wanted to prime your pump and to tickle your imagination, to make you think about Raman applications in general, and this Raman system in particular, as a tool to solve the problem that has been burning under your fingernails. I hope I could convince you that this XS system is not a Raman toy, but a serious, stable, scientific, pocket-sized platform with an easy-to-use app ready to build upon. Just add your front-end accessory and your back-end analysis, and you have created your very own Raman solution. I'm sure that the XS can also turn your Raman ideas into a reality. Thank you for your attention.
Thank you so much, Dieter, for introducing a pocket-sized Raman solution for real-world problems. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Raman Spectroscopy Summit. Thank you all so much for joining us.